This is a data set about Maize and maize growth, which is used for regression and correlation. So you have two variables. The first one is development, so the size of the plant, and the second one is the soil temperature. So if you go into variable view, you can have a look at those. So development is a scale measure. Soil temperature again is a scale measure. You've got two things which are scale measures. So in this case, it's got to be a regression because there's no grouping variable. So it can't be t-test, it can't be non-parametric test, it can't be ANOVA. It has to be a regression. And if I go back to see the data, you see in general, as the temperature goes up, the amount of development goes up. So let's have a look at the regression itself. Well, you could first plot a graph. So if you go to chart builder and you go, let's switch this off in future, it just wants to make sure that the variables are correctly defined. So they are both scalar, so that's all good, because if you've misdefined your variables, then it won't do the correct plot for you. So you drag, click down to do scatter plot, drag the scatter plot into here, and then pick your variables. Now, which one of them should go on the x-axis? Which things affecting the other? Which things causing the other thing to happen? So soil temperature is causing development to happen. So development is the dependent variable and soil temperature is the independent variable. Press OK, and I now get my graph. If I double click on that, up here there's add fit to the total. Here's add an interpolation line. So let's add a straight interpolation. Let's add a projection line. Actually, I don't want to do that. I don't want to interpolate it. Let's undo that. What I want to do is fit a regression line. So let's put a regression line through it. Now this is important because everything you're going to calculate is already in there, in that graph now. So you can see y equals 0.07 plus 9.48 e to the minus 3 times x. So this is the constant, that's the intercept where it crosses the axis. Then 9.84 times 10 to the minus 3x is the slope, so that's the gradient. And this is the r squared, which is the square of the correlation. Now that's not the proper way of doing a correlation. The proper way of doing a correlation and a regression is go to analyze, go down to regression. Now you're doing a linear regression. You're fitting a line through a set of data. So click on linear regression. So I said before, the dependent variable, the outcome, the thing you're causing to happen is development. So you click that one across. The independent variable is soil temperature. Now in this case, those are the only two variables you have. For more complicated things, you can have different groups. You can divide your experiment into more complicated groups and have other properties, but we're not going to do that. That's not important in this case. Now, what you can do in statistics is you can calculate confidence intervals. That's important for your regression coefficients. Confidence intervals are important because the slope doesn't have a single value, it actually is across a range. You can work out some plots, so you can plot some things that it will calculate. So this is predicted values. These are residuals, which is the difference between the prediction and the actual value. You can have standardized and adjusted predicted values. But I'm not going to make any of those graphs. You can have save. Now it can calculate the predicted values, unstandardized. It can standardize them, which is putting it on a scale which goes between 0 and 1. It can do all these other things like adjusting them. Now you don't really want to do any of that or the studentized residuals. These are if you're going to go into more complicated analysis after you've completed the regression. But for our purposes, you don't really need to do that. It's useful to put on the unstandardized predictive values, because then you can do a line, which is the predictive values, against the line of, you can plot the predictive values on the graph, and you can also look at how they fit compared to the real values. What else is there in options? Whether you want to exclude particular values, which might be useful if you've got some outliers. What kind of style? Nope, we don't need to do that, and we're not going to do bootstraps. So the main thing you need to do is go to statistics and click on confidence intervals, and you don't really need to do any saves or anything else. So just put the confidence intervals and press OK. So what it does is it does regression, and it also does correlation at the same time. So the first thing is summarizes the model. So here is your Pearson's R-squared, and this is your correlation. So the correlation is 0.816. If you square 0.816, you get 0.666. So that's the thing that you saw earlier on the graph. R squared linear equals 0.666. There's also an adjusted R squared. Let's not worry about that. You go down and there's an ANOVA table. You don't need to think about this, apart from it's telling you that the F value is 31.895 and the significance is 0. This is telling you that there is a slope on the line, which is good. It's got a gradient. Now the next thing, the thing that's important, is this chart. This is your line. So it's saying the constant is minus 0.065. So that's the intercept, where it crosses, where x equals 0 and where it crosses the y-axis. And it's telling you that the slope, dependent on the temperature, so the thing that the row that you need to read out to find the gradient is labelled by the whatever you've put in the x-axis. So in this case, it's soil temperature. So the gradient is 0.010. But it actually, in confidence interval, is somewhere between 0.006 and 0.014. If you go back to looking at the slope, this value here is 0.0098, so it's very close to the 0.010 that is recorded here. It's just done a slightly different rounding. If I click on that value, it shows that it's actually 0.009836, but I don't want that. For the test, I just want the values that you see in the table when you look at it to start with. And that's both the regression, so if I ask for the correlation coefficient, you do 0.0816, and if I ask for regression, I'll ask for the gradient, which is 0.010.